Hi guys, can you hear me well?
Yes.
Yes.
Thank you. Thank you. You have any questions about this class so far? Any general questions? So the sapling was due this morning, right? There were some, I got some emails about students sort of asking about the general value of sapling, like what exactly we're using this for, right? So I just want to emphasize, I already mentioned that at the beginning, that sapling is not so much a way for us to test our knowledge rather than use it to gain new knowledge, right? So sapling, if you think about it, I mean, each question is worth so little compared with the rest of the points you can get on exams, for example, right? But it has a great educational value. You know, you can try different things. You can, it's a multiple attempt question, multiple attempt homework. It's an open book. You have to do it by yourself, right? So there is a limit as far as what you can do. But you can use your textbook, right? You can use your textbook. And just to clarify things, in this class, I use sapling not so much, again, as a test tube, but rather as a way to fill some gaps in things that we don't cover in lecture, right? So I don't want to rush through material in the lecture and make it very boring and make you fall asleep. Instead, I usually like to focus on a few concepts which are difficult to understand or might be interesting, and but I allow sapling to fill the gaps for material that we were not able to cover in lecture. And also you have the textbook, you know, you bought it, it's yours, so use it. Now you can use it when you do sapling homework. Obviously, look for concepts that may not have been covered in lecture, but are in the textbook. Or you can just read the textbook. You know, that's what I would do. I would just open the textbook and read it and listen to my lecture. And usually there are some differences, right? So I give you a lot of information which is not in the textbook, but it's sort of kind of information that allows you to understand the concepts a little better. Not so much data, right? More about understanding. So what I was thinking, I will maybe later this week I will work on some short practice test, where I'll include some questions that you might find on the test on September 30th on the first test, so that you have some better idea of what the test is going to look like. Since I guess you all got really, not all, but some of you got really scared of all the math you had to do on this last sapling homework. I kind of agree, there was a bit too much math. I should have cut it down a bit more. But on the other side, on the other hand, you know, doing these math problems, obviously I will not give you so many math problems on the test. You know, we don't want to waste our time doing math on an actual test, because I would like to make my tests more conceptual, right? I want you to understand things rather than using your calculator to calculate things. But on the other hand, when you do these math problems, you arrive at answers which have some meaning, right? So for example, if you calculate the equivalence point, for example, right? Or calculate how much of the amino acid is going to be ionized at particular pH, right? So these, you can do some math, but then you get an answer which must make sense to you, right? So it's kind of math which is linked to the conceptual understanding of the material. So I hope this clarifies things a little bit more. As I said, on my part, I will try to make sapling a little bit more conceptual. And on your part, just use it. Make sure that, you know, don't expect me to cover every bit of material in my lecture. It's just not possible. And rather, let's appreciate that we can actually focus on specific aspects of the material and look at them in more detail. Are there any questions regarding this? Any questions about anything? No? All right, if you do, let me know. And again, I encourage you to use the discussion forum on Canvas. It's been utilized, but not to the extent that I was hoping it would be. So please do that. Obviously, the only way you can do it is actually if you do your homework a little earlier and don't leave it until last night, right? So try to do that. Try to do things in a more timely manner, right? Start working on homeworks a little earlier, and that will give you enough time to shoot some comments back and forth between you and other students and me. So, all right. That's what I wanted to say.
I have one question. When you go into chapters, like let's say we're going into chapter 4, are you going to cover every section that's in chapter 4 that's in the book?
Not necessarily, not. Well,
can you let us know like what section you because I read through everything. It'd be nice to know like which section to just skip over.
Yeah, well, I sent you in the announcement, right? I sent you specific pages, didn't I?
Yeah, you did. But that,
yeah, so as far as the end of the chapter 3, I wasn't too keen on that. It didn't really, I know, I looked at it and it didn't really fit. I didn't like it, you know, I didn't really, it wasn't something that I would teach in the biochemistry course. And so I kind of left it.
That was chapter 3 though, right?
It was chapter 3, yeah, because kind of left it for you guys. If you wanted to read it, but it's not something that I'm gonna put on a test. I know there is one problem on sapling that I, by mistake, I forgot to take out, which actually is related to some of the material at the end of the chapter, but it's a small one. So
okay, because what you sent us to read was the structures of proteins. You're saying that's not relevant?
So I told you to read up to pages, what, 1 or 2?
Oh, I saw 92 to 102. Yeah, 92 to 102.
Yeah.
And I felt like that's like the end of chapter 3.
So this is something that we do not cover in lecture, but it's very important material. I think it's
oh, okay.
I think it's 96 to 102, right?
Yeah, the structures, right?
Yeah. Usually if I want to emphasize something, I will let you know. But in general, so the way I will put the exam together, I will basically go through my own slides and I will use Sapling to put together the exam questions, right?
Okay.
Although I do encourage you to read the book. Read the book. It's a Leninger is a classical book. A lot of people contributed this over the years, and the material presented very well. So, and you paid money for it, so take advantage of that. All right, anything else? What is the question? Does anyone know if the book is available for checkout? Well, I doubt it, but you can try. You can try to buy a used book on Amazon. But I mean, you should have it with the Sapling, right? So I don't know if you can even register for Sapling without buying a book. They will make you buy the book.
Yeah, I have the book. I just get a headache, so I was just gonna see if it was in person, but I've been reading.
Yeah, of course, the book is available. You can go on Amazon and buy a new one for $300 or however much, or a used one, or rent one for much cheaper. So, Okay, so chapter 4. So now that we know what proteins and peptides consist of, the 20 amino acids, hopefully by now we know what they look like. We can group them into 5 groups, right? We can tell their properties based on their structures. We know their names, right? We know how they will be eluted in various chromatography columns, right? We know how they size, for example, ion exchange or size exclusion chromatography, how they will behave, right? Based on how much they protonated, which groups are protonated, at what pH. So hopefully we know all that stuff. Now we're gonna put all this knowledge together and try to start predicting how proteins organize themselves in 3 dimensions. In 3 dimensions, so let me start sharing my screen. Start sharing my screen, close this. Open that. Okay, so we're gonna start with the backbone. We're gonna start with the backbone of proteins, which is a peptide bond. I already alluded to that a couple of times. I wanted you to think about the properties of the peptide bond, and we'll talk a bit more about that. So that's actually the key to understanding of how proteins fold and function. Then we'll talk about, based on the peptide bond, we'll talk about structural hierarchy in proteins. So we'll talk about particular folds, particular local structures that proteins can adopt, right? So we'll talk about alpha helices, beta pleated sheets. We'll talk about beta turns. And then once we understand that material, then we'll apply it to the structure and function of fibrous proteins. So fibrous proteins developed like collagen, developed for strength, and we will look at those. And we'll look at the globular proteins, which are primarily water soluble. Many of them are enzymes, and see how they organize themselves, again, based on these motifs, alpha helices. And then we will talk about protein folding and denaturation. Right, so we'll talk about, so as we mentioned, the proteins are synthesized on the ribosomes. They come off the ribosome as a long string of amino acids, which then organize themselves, fold in many different ways, and hopefully adopt a native fold, right? Native fold, so that's the key one. Now, just keep in mind that like organic polymers, right, proteins have lots of single bonds. And remember what happens to single bonds. The atoms can rotate about single bonds. So if you think about the number of single bonds in any protein, you can appreciate how many 3-dimensional structures proteins can adopt. Huge number, right? Huge number, and yet it's only going to be one, maybe a couple, well, mostly one, which will be important for the function of the protein, right? If the protein doesn't adopt that fold, doesn't adopt that conformation, then it's not going to be able to perform its function. All right, so we call this structure as native fold. So in general, the native fold, the only way it's going to be stabilized is through the large number of favorable interactions within the protein, right? So the protein, again, it's not going to be a linear string. It's going to be folded in some way, some kind of sphere maybe. And so there'll be lots of interactions inside that sphere that will hold it together. Because otherwise, if these interactions were not there, look what's going to happen. There's an entropy cost for folding a protein, right? Every protein, anything, wants lots of disorder, right? So if it was up to the protein wants to unfold, give rise to all sorts of bonds being exposed to aqueous medium, interacting with through hydrogen bonding with water. Amino acids non-localized, localized here, there, but nowhere in particular. Lots of disorder. And actually, there's even a number I can give you. You would think that the native fold is stabilized by a huge amount of energy. That's not correct. In fact, if you, for most proteins, if you look at delta G folded, minus delta G unfolded, in general, we're gonna get about 20 to 60 kilojoules per mole. Now, this is an extremely small number. Obviously, this is a number that is much smaller than a covalent bond. In fact, if you remember hydrogen bonding, they're on the order of 20 kilojoules per mole. So, I mean, this is mind-boggling, right? That the protein's native fold is maintained oftentimes just by a single hydrogen bond. You remove the hydrogen bond and the protein unfolds, right? Now, just to put some things in perspective. So if you have fever, right? You have high fever, and you don't treat it, what's the danger? What can happen to you?
If you don't treat it, you die.
So why? What would you die from?
Overheat. I guess your just body gets overheated.
And what?
But there's like a lot of work in your body.
So when body overheats, so what's the danger of being? What's the danger of having the body overheat?
Don't the proteins denature?
Yeah. So denaturing and unfolding, same term. I mean, means the same thing. So the proteins basically lose their native fold and native conformation. And the reason for that is because of this number I just gave you, right? You don't need much energy to denature your proteins. Oftentimes you just have enough energy to break one hydrogen bond and goodbye. The protein loses its three-dimensional structure and it loses its function. So we need lots of interactions within the protein, as many as possible to counteract this entropy, right? So the entropy is the bad guy. It's the one that will unfold the proteins for us. So here are different types of interactions that are utilized within proteins, right? So remember hydrophobic effect, we talked about that, right? So it's not really force that brings things together, but it's something that also related to entropy and solvation layer, right? So remember, so the solvent molecules, water molecules will organize themselves around hydrophobic residues, which will decrease the entropy. And so what will happen is actually what you want to happen is you want non-polar groups to cluster together. Non-polar groups cluster together. So for that reason, the inside of the protein, we find a lot of hydrophobic groups, a lot of alanines, methionines, phenylalanines, right? So they all stuck there together, avoiding the interaction with water. And that will keep the protein folded, right? That will keep, if you unfold the protein and expose all these hydrophobic groups to water, that will increase the entropy tremendously. right? Because then the water will have to organize itself around these hydrophobic groups. If you cluster them together, you minimize that. So then hydrogen bonds. Now, as far as hydrogen bonds, so let me ask you a question. So there are hydrogen bonds, obviously, on the surface of the proteins, right? So for example, you have lots of NHs, lots of carbonyls on the surface of the proteins, which will be interacting with molecules of water, with the solution, right, forming hydrogen bonds. But if our goal is to utilize these hydrogen bonds to maintain a three-dimensional structure of proteins, how can we move these hydrogen bonds inside the protein? So for example, you have an NH bond, right? NH bond on the surface of the protein, right? So it's it looks like this. NH interacting with water. Okay, how can we move this NH inside the protein and actually make it favorable for us and make it stabilize our native fold? So we want to break this hydrogen bond, right? So how can we break this hydrogen bond? What would you do? What would your strategy be?
To add heat.
You can add heat. Yes, you'll break hydrogen bond, but in terms of protein itself, if you were given the other 20 amino acids to play, what could you do? I mean, if you could change the primary structure, basically let the protein evolve to adopt a particular fold, what functional group could you use and to put it inside of the protein, for example? Okay, let me draw it for you. So basically, what would you do? You will create a hydrogen bond acceptor right there. There'll be a carbonyl group here. And then the water on the outside will lose its part. It will lose that NH. It's not going to be unhappy. It's going to continue making bonds with other molecules of water. But so what this means is that you have to maximize the number of hydrogen bond partners. In other words, if you leave a hydrogen bond, let me write this down. Do not leave the hydrogen bond forming groups by themselves, because they will want to go outside, expose themselves to water, and break the fold. Okay, let me write this down. So the number of hydrogen bonds and this will be within the protein, right? Within protein. So we're going to try to maximize that. maximized. So do not leave H bonding group unpaired. Group unpaired. Because the H bonding group, when it's unpaired, it will not be happy inside the protein and it will destabilize the native fold. Right, so H bonding acceptor will want to have an H bonding donor nearby. Make sense? All right, so as you will see in native folds, there's always all H bonds within the protein are partnered. They all have acceptors, all have donors, and donors all have acceptors. London dispersion. So here we know that we have London forces. So remember, these are based on permanent dipole. Permanent dipole. And transient or induced. Transient. Remember, permanent dipole will be between groups which already have dipole moments, right? So like we talked about serine, threonine, methionine, basically where the charges are already separated. And transient are mostly hydrophobic groups, like valine, like phenylalanine, right? So hydrocarbon containing R groups chains. And in proteins, they're actually maximized because of the distance. So they beautifully positioned close to each other at a distance of 0.3 to 0.6 nanometers. Right, so these permanent dipole and transient dipole, they will help hold the protein in the desired three-dimensional conformation. All right, and lastly, what else do we have there? Electrostatic interactions. Electrostatic interactions. So here we're talking about salt bridges. Salt bridges. Now remember, when you have two charged species interacting with each other, obviously the opposite charges will attract each other. The same charges will repel each other, right? So, but the interaction between the bridges, interaction between these charges will depend on what's known as a dielectric constant. Who remembers what the dielectric force is, or the electric constant? It's the ability of the medium to do what? So if you put charges in a medium, Does it matter if your medium is water or vacuum?
So is it the ability of it to conduct charge, that medium to conduct charge?
Well, not so much conduct, but the ability for, yeah, to propagate. Yeah, conduct charge. Well, yeah. Well, the medium doesn't really conduct charge because it's the two electric fields which interact with each other, right? If you put the two charges, but it's ability of the medium to inhibit the propagation of this electric field, right? So different mediums, especially polar mediums, they don't allow for the electric field to go far through it, right? So the electric constant is epsilon. So for example, water has a very high dielectric constant. So let's see. So polar aqueous medium, epsilon is close to 80. Now within the protein where water is excluded, right? So water doesn't, well, there is some water within proteins, but not much, right? Water, proteins kick it out because they want to be hydrophobic inside. So within proteins, oftentimes you have the dielectric constant in single digits. Within proteins, four. So the conclusion is the Soul bridges are stronger. And we will see examples in this class later when we talk about protein functions. Stronger within proteins. We will see how these Soul bridges accomplish and maintain the tertiary structure of proteins or perform an enzymatic function. Can you think of a particular Soul bridge that comes to mind? So basically remember, Soul bridges are going to be interactions between ions, right? Permanent ions that create electric fields, and hopefully they're of the opposite charge so they can attract each other. So if they have the same charge, they will repel each other, and that will destabilize the native fold. So can you think of some Soul bridges? Here's your knowledge of amino acids should help you. Tell me. Give me an example of a negatively charged amino acid, which is permanently negatively charged at normal pH 7.
That would be aspartic acid,
Oops.
glutamic acid.
Yep, 2 of them is good. So negatively charged aspartic acid, glutamic acid. How about positively charged?
Lysine?
Which one?
Lysine?
Lysine. What else?
Histidine.
Histidine, arginine. Perfect. I think that's enough. histidine, arginine. Right, so these will be permanently charged, and within the protein, if you find aspartate in close proximity to lysine, then you should expect a Sol bridge. And a Sol bridge, because of the low dielectric constant of 4, right? The Sol bridge will be very strong. It'll help stabilize the native fold. But do not put aspartate in close proximity to glutamate or two aspartates together, right? So the nature will not let the protein evolve like that, because the protein will struggle maintaining its three-dimensional structure.
Can you repeat really quickly what the 0.3 to 0.6 nanometers distance was? Is that across the
Oh, that's the approximate distance. You know, if you take in general the protein, so this will be the amino acids inside the protein core, right? So the general positioned at the distance of 0.3 to 0.6 nanometers away from each other. At that distance, these London dispersion forces are very strong. Okay.
So that's not like the length of the amide linkages. That's the distance that the London forces are strong.
Yeah, between different side chains. Mm-hmm.
Thank you.
Anything else? All right, let's move on. So in general, we'll talk about 4 levels of protein structure. So let's introduce that now. So in the previous chapter, we talked about primary structure, right? So this is the sequence of amino acids. But we know that that's not how this protein is going to look like in real life. In real life, it will adopt multiple levels of structure. The secondary structure will be some kind of local structure, which is going to spread over short distances. Okay. And so, for example, here it will be alpha helix. So we'll talk about alpha helix later in this lecture today. So, but then these alpha helices, they can fold all together, right? So there's some kind of alpha helix, there's some kind of connection, some kind of ribbon or random coil, then another alpha helix. I don't know what that is. Some kind of prosthetic group maybe. So another alpha helix there, right? So the tertiary structure is basically how these local secondary structures organize relative to each other, right? So that will be the tertiary structure and secondary structure. And finally, once you have that, the proteins can assemble into larger multi-subunit proteins, and that will be called quaternary structure. So in many cases, these subunits are non-covalently associated, right, through some kind of non-covalent interactions. And in many cases, these kind of proteins are oligomers. So what that means is that each of the subunit is the same. In many other cases, they're different. And so this will be quaternary structure. So we'll have some examples of proteins like that as well. Okay. 3 levels of protein structure. All right, so we'll start our discussion of the peptide bond. So that's where it all starts, right? So each protein backbone will have a peptide in it. And so fundamentally, the structure of a protein will be in great part dictated by the properties of the peptide bond. Okay, so it's a resonance hybrid of 2 canonical structures. So we'll talk about that in just in a moment. And for example, because of this resonance, I already told you, and you can think some more about it. The peptide bonds are much less reactive compared with esters, right? So I told you that the proteins are much more stable than polyester proteins, right? So if you have a polyester polymer, it's biodegradable, you put it in the bloodstream, and it's going to be cleaved by the enzymes known as esterases, which will highly efficient, and esters are very unstable. They will cleave the esters very quickly. But for the peptide bonds are much stronger. Now they're also rigid and nearly planar and exhibit large dipole moment in a favored trans configuration. So let's look at that. So here we have a peptide bond. So the key to understanding the peptide bond is this resonance. We already looked at that before, right? So there is a double bond character between carbon and nitrogen. So in this structure we have a single bond. In next structure we have double bond, right? So in reality it's somewhere in between. And note the type of arrow we're gonna use between resonance structures. Something for you to remember from organic chemistry, where I like to take some points off if students tell me that these are the same or interchangeable. What's the difference between this kind of arrow and this kind of arrow?
Resonance versus equilibrium.
Resonance versus equilibrium. So here you have two different compounds, A and B, right? Whereas resonance is the same compound. It's just two different representations, right? You can have electrons, you can show the electrons to be localized here, or you can show the electrons to be localized on the oxygen. In reality, they're not here, they're not there, they're somewhere in between. They're just electron cloud, which is present everywhere in this molecule. Electron density may be a little different, right? So that it's possible that there's just electron density is slightly higher on the oxygen than it is on the nitrogen, or vice versa. I'm not exactly sure. The quantum mechanical calculations should tell us, but it doesn't matter. It's the same compound, right? It's just the distribution of electrons which can be shown using two AND structures. And also, obviously, you can consider another resonance structure where nitrogen takes away its two electrons and leaves the empty orbital on the carbon. And so the carbon will be positively charged. So, so it's polar. It's polar because of the contribution of this resonance structure. It's also rigid. What does rigidity mean? Rigid. It's rigid because there is no free rotation about carbon-nitrogen double bond or carbon-nitrogen partial double bond in a peptide bond. No rotation. No rotation. And also one other thing for us to keep in mind is that, look at that. There is the angle here. Now this is looking in this direction, and this is looking in this direction, right? So the angle between the two alpha carbons is 180 degrees. This is something for us to keep in mind, right? So so the two carbons. So if we have a Newman projection, right? Then let's say if the front is carbon, the back is nitrogen, then this, let's label this C alpha prime and C alpha double prime, right? So from the nitrogen, we'll have C alpha double prime, and from the carbon, we'll have C alpha prime, right? So they're totally anti to each other, the opposite. So the angle is 180 degrees. And that's because of stereohindrance. And as we will see, the peptides like this kind of orientation where the two alpha carbons are far away from each other. And keep in mind, these are not just carbons, right? So there are side chains. Each alpha carbon will have a huge group R. So these groups R will want to be as far away from each other as possible. Okay, any questions about the peptide bond? All right. So resonance is key to understanding many of the protein structures. All right, so rotation about the peptide bond is not permitted due to resonance structure. I just showed you. But rotation around bonds connected to the alpha carbon is permitted. There'll be one phi and the other one will be psi. And the fully extended polypeptide, both psi and phi, are 180 degrees. All right, so let's look at that. Let's look at that. So here is our peptide bond that we're going to look at, right? So you can see that each peptide bond, so here we have one alpha carbon, carbon of the carbonyl, oxygen of the carbonyl, nitrogen of the amide, hydrogen of the amide, and the alpha carbon on the other side. So each peptide bond engages 6 atoms. And you can see here, so we have, for example, distances. So let's say the distance between this alpha carbon and the carbonyl is 1.53 angstroms. Now remind me, how many meters is 1 angstrom? How many meters? You should know. How many meters is 1 angstrom? So angstrom is a unit, length unit, utilized primarily by crystallographers. And you can see why it's useful is because you can measure interatomic distances using numbers which are close to 1, just slightly larger to 1. Very convenient number to use, right? No logs, no no exponents, right? No exponents, no logs, nothing. Just one number which is convenient to use. So how much is 1 angstrom?
1 times 10 to the negative 10.
Perfect. 10 to the negative 10 meters. And if you like to prefer to work with nanometers, it's 0.1 nanometer. Right, so this angle, this length here is 1.53 angstroms. And this length between the two atoms of a single bond is 1.56. So you can see the double bonds, which are shorter, right? So we talked about that in general chemistry and in organic chemistry. So double bonds are shorter than single bonds. So you can see that this double bond is 1.24 angstroms. And then a peptide bond, carbon-nitrogen bond. So this bond has partial double bond character. So it's in between, right? It's not as long as 1.5 and it's not as short as 1.2. So there's significant partial double bond character between carbon and nitrogen of the peptide bond. due to resonance. All right, and so you can see that there are three, if you look at the peptide bond in general, so there are three bonds which are repeating the cycle, right? So we're going from alpha carbon, carbon of the carbonyl, nitrogen of the peptide, next alpha carbon. So we just went through three bonds. Again, carbon of the peptide, nitrogen of the peptide, next alpha carbon. Carbon of the peptide, nitrogen of the peptide, next alpha carbon, right? So any peptide backbone will consist of these three bonds. And so as far as rotation, so it's a rotation about these bonds, which will tell us the three-dimensional structure of proteins. But we're only going to look at two out of these three. Now there's a third one. So obviously this one. And in general, so this is referred to as omega. But omega is always 180 degrees. We will look at some exceptions to this when it comes to proline, amino acid proline. Sometimes proline likes to adopt other angles, and it likes to adopt 0 degrees, but this is 180. So what that means, again, this is in this direction, this is in this direction, and omega is always 180 because of the partial double bond character. There'll be no free rotation about this bond. So omega is always 180, but phi and psi, they can adopt a bunch of different angles. So these are known as dihedral angles. So phi and psi, phi and psi, dihedral angles. And as I mentioned to you, peptides like to adopt this extended conformation. An extended also commonly referred to as zigzag. Zigzag conformation. Phi and psi are 180 degrees. Okay, so you can see here. So phi will be the angle between the nitrogen of the alpha carbon and the alpha carbon. And you can see the two bonds of the peptide backbone, they are trans to each other, right? And the psi for the same thing. Now the alpha carbon on the other side. So that's going to be the bond between the this part of the peptide backbone on the other side of the carbonyl and this nitrogen, right? It's 180 degrees. All right, so these are the main properties of the peptide backbone, right? And you can see here what this allows one to do is also the R group is on this side and this R group on that side, this side, that side, this side, that side. So the zigzag conformation is also favorable, stabilized by the fact that the side chains are separated from each other sterically, right? So they're not in steric congestion. All right, any question about the general?
Is there ever a case where there is like a cis peptide bond, or is it
Yeah.
always trans?
Well, in general, it will be trans, right? In 99.96 something, I'll actually give you the actual number later. In that number of cases, it's always going to be trans, but with proline, amino acid proline is an exception. right? So we will see the we will see that in beta turns, proline often adopts angles which are other than 180. Proline is an exception. Okay. So you may think that so this would be the ideal distribution of these phi and psi angles, but there are many other factors in proteins and enzymes, right? And so that gives rise to some favorable and unfavorable phi and psi combinations, right? So for a particular set of phi, you may find some specific psi combinations, which, sorry, specific psi values, which go along much better with specific phi numbers. So oftentimes this is because of steric crowding of the backbone atoms, okay? And so we're gonna look at that. And also some of them are favored because of favorable hydrogen bonding interactions, right? So trans is good. Trans is good because it moves the backbone chain in the most puts the backbone chain in the most favorable orientation, but there are other things to look at. There is steric crowding and there is favorable H bonding interaction. And so there was a scientist, Ramachandran, who actually proposed to use a plot which would show the distribution of these phi and psi dihedral angles that are found in proteins. And depending on where on that plot you find your local three-dimensional structure, local motif, it will tell you which one it is, okay? So let's look at that. So this is the Ramachandran plot. So here we have available phi angles, right? From minus 180, one anti to the other end, to the same one, from minus 180 to plus 180. So 0 will be cis, right? So this is trans, cis, trans again. So the cycle will start here. And this is favorable psi degrees, okay? So we will talk about these different three-dimensional conformations. And you can see here, so we'll talk next about alpha helix. And you can see that alpha helix, the proteins which adopt the alpha helix conformation, their combination of phi and psi will be found in this region of the Ramachandran plot. So actually the darker the blue, the more favorable it is, right? So lighter blue is less favorable. Lighter blue is less favorable. So there's a very high chance that the alpha helix angles will be found in this area of the Ramachandran plot. So then there's anti-parallel beta sheets, parallel beta sheets, collagen triple helix. So we'll find that triple helix is slightly different from alpha helix, and it's found all the way up there. This is left-handed alpha helix. It's found over here. But in general, you can see actually that it's a very small area which is occupied by all the proteins, by the various three-dimensional structures on the Ramachandran plot. Most of it, like this area here, is inaccessible, which means you will find no proteins which have, for example, a combination of, let's say this one, we'll find a combination of minus 120 of psi and minus one plus whatever 120 or minus 110, right? So this combination will never be found in a protein, and that's for a number of reasons. Again, steric hindrance, lack of hydrogen bonding, right?
Is this one peptide bond or what? I don't know what I'm looking at.
So these are the combination of secondary structures. So basically the combination of psi and phi angles that lead to a particular secondary structure. So once we start talking about secondary structures, it will become more clear.
Oh, okay, okay.
So for now, you're just looking at various possible combinations of psi and phi, which proteins can adopt.
Okay.
So what this plot is saying is that for majority of it, these combinations of phi and psi are not accessible and have never been found in proteins. All right. So now this is, let's see what this is. This is, hold on a second. Okay, so this enzyme is pyruvate kinase. It must be in a legend. I just don't have the legend in this presentation. Pyruvate kinase. And so these various dots on it are specific amino acid residues. So each dot is a particular amino acid residue. And so each amino acid residue you can see is found within the region of the allowable psi and phi combinations, right? It just shows you how Ramachandran plot is basically telling us that indeed, it doesn't matter. Just pick any protein, and any amino acid that you find in that protein will be either here in this region, or this left-handed alpha helix, this region, and there's something in the bottom here. Which one is that? Did we have that before? It doesn't say what this region here is, minus 180. So this must be close to the extended conformation, right? If they're both close to minus 180. So I'll write this down. I'll put zigzag, but I'll double check. It's not on my slide and it's not in a book. So just because they're close to 180, that's just my assumption that they're close to the zigzag conformation. So these are different amino acids in the enzyme pyruvate kinase, and you can see they occupy various allowable psi and phi combinations, right? So one thing which is excluded from this is glycines. So in fact, you can find glycines far out of the allowable conformations. And the reason for that is because, what do you think the reason for that is? Why does glycine usually, is an amino acid that doesn't conform with the rules?
Is it because it doesn't have an R group?
Doesn't have an R group, and so what does that do?
It doesn't have to be L or D. It can be both.
Right. So it's good that you mentioned as far as L and D. Right. So when we talk about the alpha helix, right? You have to have consistency with which amino acids you're dealing with. It has to be either L or D, not both. Right. So glycine basically doesn't have an R group, and so there is no steric hindrance involved there. Right. If steric hindrance is part of what actually drives the formation of all these secondary structures, then glycine just doesn't care. It says, I don't have an R group, I don't have a side chain, I don't need to worry about steric hindrance, I can be found anywhere. My psi and phi dihedral angles can adopt different combinations outside of the normally found regions, right? Okay. All right, so there was a scientist, Linus Pauling. Linus Pauling, very famous scientist, received 2 Nobel Prizes, one in chemistry, one in peace. Linus Pauling. Who was a visiting professor at Oxford, got ill, was staying at home for a couple of days, and instead of reading some fiction story, he decided to play with the structure of different proteins and came up with the structure of the alpha helix, and claimed that many proteins love to adopt the alpha helixes. So, so the most common will be alpha helix. So this is stabilized by hydrogen bonds between nearby residues. So we'll talk about beta sheet, stabilized by hydrogen bonds between adjacent segments that may not be nearby, right? So alpha helix is a more local, beta sheet is a more distant, right? So the beta sheet, you can find, you know, the protein chain starts from beta sheet and goes for a walk somewhere, you know, makes a few loops here and there, and then comes back and forms favorable interaction with the segment that we started with. So, so not adjacent segment, it may not be nearby, and these are nearby, so important. And then there's irregular arrangements of polypeptide chain, which are neither of these, oftentimes called random coil. And so here are the most favorable combinations of phi and psi for these structures, right? So now I don't want you to memorize this, but just for you to have this table in front of you, if you need it to solve some sampling problems, will be useful. So helix, -57, -47. Now there's beta sheets, anti-parallel, parallel. There's collagen triple helix. We'll find that it's actually quite different from the other helix. There's beta turns type 1, and beta turn type 2. So we'll look at both. All right. So here's the alpha helix. So basically, it's a helical backbone, right? Which is now the backbone, which is held together by hydrogen bonds between the backbone amides of an N and N+4 amino acids. So let's look for those. Let's start at the bottom here. So here's the carboxyl terminus, right? The carboxylic acid is here. So here's the NH of the peptide. NH of the peptide. Then we go through the one peptide, alpha carbon, the R group, nitrogen, carbonyl, alpha carbon of the next one, nitrogen carbonyl, alpha carbon behind, we don't see it here, and then the carbonyl, and now the carbonyl of the N+4. So if this was N, then 4 amino acids later, there will be a carbonyl group that forms a hydrogen bond with the NH. So this is hydrogen bond donor, H bond, donor, and on top the carbonyl is the acceptor. acceptor. And then the same thing the same situation repeats itself again. Then we have another amino acid residue, and then the NH again forms a hydrogen bond with a carbonyl of an amino acid, which is 4 amino acids down the line, down the backbone. Okay, specifically, actually, because it's NH and a carbonyl, it's 3.6 residues. So this hydrogen bond occurs every 3.6 residues. Okay, so so what this means now, let me ask you then this. So how many residues, how many amino acid residues will be in a segment in alpha helix? Let's say you have alpha helix with 10 turns. 10 turns. How many amino acids will it contain? So this
is it about 30?
36?
36, more precisely,
36.
correct. Right, so if it turned around 10 times, 3.6 times 10 will be 36 amino acids. 36 amino acids. Because 3.6 is kind of a difficult number to deal with because it doesn't really represent the reality, right? But, so each turn is also associated with 5.4 angstroms, right? So this is the distance between where it begins, the turn begins, and that's where the turn ends, 3.6 angstroms. Sorry, 5.4 angstroms. So, so it's a right-handed helix, 3.6 residues, peptide bonds are aligned, roughly parallel with the helical axis, and side chains point out and roughly perpendicular to the helical axis. So side chains are here, side chain there, side chain there, side chain there, right? Basically side chain is kind of for the sticking out in a horizontal direction away from the alpha helix. And that helps them avoid the steric crowding, right? They don't have to be buried within this alpha helix, interacting with all other amino acids. They're just sticking out and doing their own thing. And this is how you would determine the alpha helix, sorry, the left-handed and right-handed alpha helix. So this is the rule of thumb. Yeah, the way I actually look at this, if this is my direction of propagation of my alpha helix, right? If it goes in a clockwise direction, clockwise, it's right-handed. Clockwise. And so obviously counterclockwise will be left-handed. So, so what we saw here, this was the right-handed alpha helix. All right. So this is just the view from the top. View from the top. You can see that these R groups are sticking out right in the horizontal direction, away from each other. And you can see here that actually the inside of the alpha helix is actually quite packed with the amino acid, with the peptide backbone, right? And the R groups are on the outside. The R groups on the outside. And here is this another representation. So we start with the amino acid 1, 2, 3, 4, 5, 6, 7, kind of going away from us in the right-handed alpha helix to amino acid 11. So you can also actually already start noticing what will stabilize. Now, by looking at this structure, before we go to the next slide, what do you, I mean, something is already drawn here that will tell you tell you what will stabilize alpha helix. Like what is on this picture?
Isn't it the hydrogen bonding?
What kind of hydrogen bonding? Well,
Well,
hydrogen bonding,
this-
no, hydrogen bonding is already there. It's not actually, well, not shown here, but yes, hydrogen bonding, obviously. But I mean, you will have hydrogen bonding, I mean, other than proline, amino acid proline, all the other amino acids will have NHs and the carbonyls, right?
Mhm.
So all the other amino acids will allow you to allow for the alpha helix formation. But there is something here, something on this picture, find it, that will tell you, give you some information as far as how you can stabilize the alpha helix. Something on this picture that I have not mentioned yet. What is it?
Is it the positive and negative charges?
So what do they represent?
The amino group and the carboxyl.
So it tells you about the type of amino acid that you want to put here, correct? So in other words, if your amino acid 1 is a lysine, which will be protonated, if your amino acid 4 is glutamate, which will be deprotonated, then that kind of positioning will stabilize alpha helix, right? So this is something that you will learn later also in this class. I will keep quizzing you on that. So for example, if I have a sequence of a peptide sequence where my amino acid 1 is lysine, my amino acid 4 is glutamate, my amino acid 7 is, what should be my amino acid 7? How about arginine? Arginine. So in other words, if I have alternating charges every 3 amino acids, that should stabilize the alpha helix, right? So that kind of combination of amino acids will stabilize. What if in positions 1, 4, 7, 10, 13, if I have glutamates, will that protein adopt alpha helix?
No.
No, because then the negative charges will repel each other. Right, so you know already some things about how to stabilize, how to destabilize alpha helix. So let's see, we'll talk more about the how to stabilize, destabilize alpha helix in the lecture on Wednesday. I think I would like to stop now. We're getting very close to the end. Are there any questions so far? I'll open the sapling homework so you can start working on that. Throw some questions for the discussion forum. And any other questions?
I have a quick one. I think one of the case studies was for this chapter. Is that right?
Case study on sapling?
Yeah, I think I completed it and then I realized I think it was with Unit 4. Is that right? That we should be doing, I think the first case study. I'm not sure how many case studies were in there, but I think at least the first one is this unit.
Oh, you know,
is
I
that
haven't
right?
looked at, this is something for me that it's something that I'll be doing today. I haven't looked
Okay.
at the sapling homeworks for this chapter yet. But I think you're right. I think there is a case study there.
Okay, great. Thank you.
Yeah. Okay. All right. Well, let me know how it goes. And I'll see you on Wednesday. Bye. Stay healthy.
Thank you.